In Premier Field Engineering, there is an emphasis on deep dives in Level 400 material. This is appropriate because engineers are hired based on their existing knowledge of products and technologies. Almost no one, however, is hired because of their experience with SQL Server Analysis Services multidimensional expressions. And there are those who are familiar with SQL Server Analysis Services in general that are not proficient in MDX. SSAS and MDX are separate skill sets. Many engineers that support SSAS in the support queues do not assist customers or PFEs with MDX questions. When you request assistance through these queues, specify MDX rather than SSAS generally when looking for an engineer with MDX knowledge. Because it seems difficult to even begin a study of MDX, a discussion of lowest level MDX fundamentals can yield a benefit that would not be an appropriate level of discussion among PFEs of other Microsoft technologies. This video is a discussion of these lowest level MDX fundamentals. Most books on MDX focus on MDX functions in the concept of queries and seem to expect the reader to intuitively fill in the blanks about dimensional concepts. This gives an incomplete understanding of the syntax of MDX, and the student is therefore seldom comfortable with the core concepts. The question, why doesn't the where clause in an MDX select query have an equals sign in it, like a SQL query does, begins to describe the confusion I felt initially, and I thought it ought to be so obvious a question that everyone should be answering it in their discussions of MDX for beginners. Now I know the answer, and I will give the answer later in this video. You will be able to be more patient with yourself and others if we explicitly articulate some of the reasons that MDX is more difficult to learn than SQL. MDX is not SQL, but comparing some of their features can be illustrative. In a SQL statement, we can fully qualify the names of objects, such as tables, views, and stored procedures, using syntax such as this. We know that we have a default schema name, but in general, if we start dropping parts from the fully qualified name so that they will be inferred by SQL Server's parser, we omit them from left to right in order. In SQL, it is meaningless to include everything but the specific object name in a query, such as in this example. In contrast, in MDX we often have a fully qualified member name such as this. We find that we can often eliminate each part or multiple parts or most parts or in some cases all parts of the fully qualified name so long as the relative order of the ones that remain is maintained. For an SSAS database cube we will be viewing shortly, any one of the following expressions will yield the same result. I don't think I've gotten them all, but at this point, none of these expressions need to mean anything to you. But this example is intended merely to make the point that being flexible implies having to understand the nuances of having many ways of doing the same thing. Don't be misled into thinking that there are so many ways of saying something that it's hard to make a syntax error. It turns out that I could also list a great many things that appear very similar to this list that, while not generating an error, won't give you the answer you want either. We will be explaining the ampersands contained in these expressions later in this video as well. When SQL Server parses a query, it uses the database metadata to supply missing portions of a fully qualified name. Due to the nature of SQL, the actual data in the tables does not assist in determining whether the syntax of the SQL query is valid. The query optimizer is interested in available indexes and statistics about the distribution of the data, but the actual validity of the syntax of the query is determined by the metadata of the database. In the case of MDX, we can have queries such as the following, which reference virtually no metadata at all, other than the cube name. And yet the SSAS formula engine will scour the actual data in the SSAS database cube at query time to determine if there is a way to supply metadata that will make the query valid. This approach provides a flexible way to write MDX queries, But the flexibility has two important consequences when we try to understand MDX. The first is that the formula engine has to have additional code to parse and resolve objects that are not fully qualified, to the point of interrogating the cube about actual data in the cube to determine the meaning of the query. And second, we as MDX writers, readers, and debuggers must be aware of these additional rules that make for greater flexibility in the writing of MDX statements. Flexibility may be good for MDX experts, but it adds complexity to the rules for parsing MDX, which rules we must understand if we are going to be comfortable with the seemingly infinite variations on syntax which we might see for the same statement. My expectation is that once you gain experience with MDX, you will come to realize that despite its flexibility, it is the least forgiving and most frustrating computer language you will ever encounter. While the factors that make it unforgiving and frustrating are present to some degree in other languages and environments, these factors seem to be exaggerated in MDX. MDX is about getting data out of a data structure known as a cube, viewing the data in meaningful configurations, and manipulating the data. Querying a cube means asking what values are contained in cells within the cube. We must have a way of specifying which cells we wish to include in a result, so we must be able to navigate the cube to indicate locations. Because we navigate cubes in a way that is similar to the way that we navigate spatial dimensions, let's start with the spatial dimensions that we know and discover the differences between spatial dimensions and MDX dimensions. When we have a Cartesian coordinate system with spatial axes, there are several notations we can use to identify a point in space. For simplicity, let's consider two-dimensional space, although the concepts we are discussing can be extended to any number of dimensions, even though space has only 3 dimensions. We could specify an ordered coordinate where the position of each coordinate's value identifies which axis it is associated with. This is the traditional notation for spatial dimensions, with which you are almost certainly familiar. The first position will always represent the value of the x-coordinate, and the second the y-coordinate. Recognize that although I have limited my sample to integer values of the coordinates, the x and y coordinates in space are continuous and could represent any real number, such as 2.257. If we wish to have the flexibility of expressing the spatial coordinate values in an arbitrary order, or we wish to be able to omit references to one or more coordinate values, we could specify the values for their associated axes in at least 2 other ways. One is by using an equal sign. This is reminiscent of what developers might call named parameters when passing parameters to a function in an arbitrary order. And this also permits the omission of a parameter entirely, which is generally not possible when passing parameters to a function through the order of the parameters. The functions must have some built-in behavior to handle the situation where parameters are omitted. Another way of specifying the coordinate is by using dotted notation. This third notation is close to the one that is used in MDX to represent the intersection of the values of dimensions. The dimension name is part of the value. The expressions, called tuples, shown on this slide, all describe the same location. In MDX, the values allowed along an axis are called members and will seldom be numeric. They will normally be textual and descriptive. If the value along an axis is a number, however, it is not a valid representation of a member of an MDX dimension unless it is placed in square brackets. Members of an MDX dimension that are described by numbers must be placed in square brackets. The dimension names, or axis names, may also be placed in square brackets and must be placed in square brackets if the dimension name contains a space or some other special character. This is very similar to the rule for placing, for example, object names in square brackets within the definition of objects using TSQL in the SQL Server relational database. Very often, we'll just go ahead and put square brackets around each part of a dimension name and member for the sake of consistency. Here is a grid which is more representative of the type of data we might find in an analysis services cube, but still, it is not realistic. It does not have a time dimension, and every useful cube I've ever encountered does have one. We'll add a time dimension later. Notice that instead of an x-axis, we have a geography axis. Instead of a y-axis, we have a focus axis. The values these axes can take on, or their members, are not continuous numeric values, as we saw with Cartesian coordinates, but discrete string values. The intersection of the members of the dimensions is not a point, but a cell. Each cell can contain exactly one numeric value. The value of a cell is not going to be Joe or SQL Server or Missouri. It is going to be a number. If there are exceptions to this rule, we are not going to discuss them. Notice that Missouri has only one SQL Server PFE. The other cells will have values, but they are not displayed. How do we reference the cell that contains the number of SQL Server PFEs in Missouri? One way is to use a tuple that shows the member of the geography dimension and the member of the focus dimension in either order. The member SQL Server must be surrounded by square brackets because it contains a space. Notice in the third pair of tuples, the dimensions are not explicitly shown at all. That's because the values in these tuples are unique across the entire cube and unambiguous, and the analysis services formula engine takes the effort to search through dimensions and members, as well as hierarchies and levels, which we will discuss later, in order to find objects that make the expressions meaningful. It does take some computational effort to do this, however, so the shorthand notation may be introducing some latency in the execution of a query that uses such a shorthanded notation. This notation is confusing for users who are not intimately familiar with the nature of the data and the structure of the dimensions and measures. What does it mean when a tuple does not explicitly reference every dimension in a cube? Because the interpretation of a cube or cell actually requires the intersection of members from every dimension associated with the cube, including the measures dimension. A member, known as the default member, is implicit for those dimensions that do not have an explicitly referenced member. The default member is usually the all member, but does not have to be. The designer of an analysis services database may specify that some dimensions do not have an all member. The time dimension seldom has an all member. The measures dimension never has an all member. The default member can be specified by the developer of the SSAS database, or it will be supplied by SSAS itself if the developer does not supply one. There is only one default measure in a cube, regardless of the number of fact tables or measure groups in the cube. The default member of a dimension selected by analysis services may be dependent upon the sort order of the language being used, and if additional members are added to a dimension over time, the default member selected by analysis services may change during processing, yielding unpredictable and confusing results. Therefore, it is a good idea to specify a default member for each dimension so that it has a known value. I have observed the phenomenon of a default member that changed over time with a customer who believed that additional processing of their cube was revealing a bug. In fact, additional processing was adding members to a dimension, and SSAS was changing the default member based on its own internal algorithm. We are not entitled to rely upon analysis services using the same method of selecting a default member from version to version of analysis services when we fail to choose a default member. The grid showing the number of PFEs in a region appears to be a two-dimensional grid because it contains geography and focus along its two axes. But it is different than a Cartesian two-dimensional grid because the intersection of the members has a value in it, and that value is measuring something. It becomes more apparent that the measure is a third dimension if we look at multiple grids measuring different things. In this case, number of PFEs, years of experience, and number of certifications, realizing that each of the cells of those grids contains values, all of them numeric, and that if we stack the grids on top of each other, as we see at the bottom, with the measures coming toward us on the z-axis, we in fact have a three-dimensional grid. We loosely call this a cube regardless of the number of dimensions in the structure, and regardless of the number of members of each dimension, because each cell is a unique intersection of dimension members. Each cell can only contain one numeric value at a time. We must add another member to the measures dimension if we wish to record another type of measurement. Even if we have only one measure, the measures dimension is the third dimension of this grid. For some time, I've heard that measures are really just another kind of dimension, but it never really quite made sense to me until I realized that the members of the non-measure dimensions and the members of the measure dimension are stored differently in the star schema relational database. If we add members to a non-measure dimension, we must add rows to a dimension table in the star schema relational database. Adding members to a measure corresponds to adding columns to the fact table in a star schema relational database. Adding members to non-measure dimensions does not change the schema of the star schema relational database, but adding members to measures does change the schema. In ordinary conversation, we almost always say dimensions without meaning to include measures. But one must look to the context to see whether measures are intended when someone refers to dimensions in general. It is not usually difficult to figure out. In this video, I am trying to clearly distinguish between non-measure dimensions and measure dimensions in a way that you will eventually find annoying. We need more than just dimensions and members in MDX Expressions to refer to the data in a cube. There are also hierarchies and levels. And to get insight into these, it will help to observe the design and building of a simple cube while we highlight some of the decisions that we can make while we do so. This is Microsoft Business Intelligence Development Studio. It looks like Microsoft Visual Studio because it is. The two are the same, just that the environment we have here has some additional tools installed for working with SQL Server technologies. We're going to go in and create a new project. We'll give it a name. And it populates Solution Explorer with a tree view where we can create objects for the project. The first thing I'll do is create a data source. Going to select Inherit as the impersonation type. When you are just trying to get bids to work with SSAS and SQL Server, even where most or all components are installed on one machine, the security impersonation screen can be rather frustrating. If you select the wrong thing here, you may not see an error until after you design and build your project and attempt to deploy an SSAS database to an SSAS server. Just to get things to work, picking Inherit in SSAS 2008 or Default in SSAS 2005 on this screen is most likely to get you up and running with the least amount of thought and effort. When you analyze the situation more generally, you will realize that using BIDs, you are likely to already have things set up so that you, as an SSAS developer, have appropriate rights to the SQL Server Relational Data Warehouse and the SQL Server Analysis Services service that you are using. This screen is asking what account the SSAS service should use to access the SQL Server Star Schema Relational Data Warehouse. Thinking it through after you've already got one configuration to work is easier than making it work the first time. These issues are similar to those in a web development environment where the developer using Visual Studio must have the correct security access to the IIS service and to SQL Server. But rights must also be assigned to the IIS service to access SQL Server for actually running the web application.
I'm going to give it a name, although you can tell from the extension on the file it's going to create what type of object it is. I like to go ahead and give these things different names. Otherwise, you'll wind up with a data source, data view, and cube, all that have the same name. There's nothing wrong with that. I just prefer not to. Now we have a data source. Let's create a data source view. We'll add all the tables except the one associated with database diagrams. And we'll give it a meaningful name also.
The data view is the child of Microsoft's Unified Dimensional Model, or UDM. One of the goals of using the data view seemed to be to provide the opportunity to provide a layer of abstraction that might permit the population of a cube directly from heterogeneous data sources without the creation of a star schema relational database. With experience, you will probably decide this is not a good idea. However, data views are still very powerful tools for tweaking the data that is pulled into an SSAS database cube from a star schema relational database data warehouse.
Here we have a data source view. The interesting feature of the data source view is that we can explore the data without going back to SQL Server Management Studio. And there are some other very interesting things we can do here that are beyond the scope of this discussion. All we're going to do is use it to remind ourselves of the structure of the data. Now, we could create a cube using the cube wizard that would create the dimensions for us. However, I want to make some different decisions than it would make in designing our dimensions. So I'm going to create the dimensions first. I'm going to use the dimension wizard. It is going to have this dimension, the first one we're going to create, based on an existing table. And we can select that table. If the table is not visible, it's very possible that we have more than one data source view and the correct one is not selected. Here we only have one data source view. So I'm going to pick the focus as the main table of our dimension. I'm going to leave the name column as focus ID. And notice that when I do that, it takes the other column in the table, which is focus, and makes it available to include in the dimension. Notice it says we're selecting this to surface it as a hierarchy. We'll see more of what that means in a moment. Notice it is calling the columns in the underlying star schema relational database dimension table an attribute. and we'll go ahead and leave this selected with the name of focus, and we'll finish. Now, it's possible to build, deploy, and process a dimension without having an entire cube, and that's what we're going to do, and we're going to do it in one step. If I suggest to process it, it is going to go ahead and figure out that it needs to build and deploy it as well, so it's going to take all the steps we need. During this video, I will be skipping over the building, deploying, and processing step most of the time, so you may not even see it flash by. Now, let's go into the browser and browse this, paying careful attention to the terminology. We are on a tab for the focus dimension. It has a combo box where we can select hierarchy. So within the focus dimension, there are two hierarchies which have the same names as the attributes that we selected from the underlying relational database dimension table. Notice that if we select focus and come over here, we can expand the tree and see the values that we had in the table for the focus column. It has added an unknown column, which was not one of the data elements. And notice it has an all up here as well. When I click on the word all, which also did not appear in our data, it says current level is all with parentheses around it. When I select on one of the values of the focus attribute, notice it changes to focus. So we have two levels here. We have a dimension, which is focus. We have a hierarchy, which is focus. We have a level, which is either all or focus. And we have values in here. So what are the ways that we could write this? Now let's look at the focus ID, and we'll see it has an all level as well. It has another level called focus ID. So to dig down to this value of 1, we would have the focus dimension, the focus ID hierarchy, the focus ID level, and then the actual member value. Now let's go and create the geography dimension and make a different selection for one of the important choices we can make. Instead of leaving the name column as geography ID, whereas I left the name column for focus as focus ID, I'm going to change it to state. Once I do that, we'll see state no longer appears as an attribute that we can select under available attributes. That's because it must be included since it's going to be the name. If we were to come back here and change this back to geography ID, we'd see that it was available, and this would correspond to the situation we just saw with focus. But I'm going to come back and make this state, and we'll see that state is not available. It won't let us uncheck the geography ID box. We have selected that as the key. And so now we're going to leave this name as geography, and we'll go ahead and finish the wizard. Let's go ahead and process the geography dimension as well, and then browse it. Notice that we have the geography dimension here. Under hierarchies, we only see one hierarchy. And if we come down, we'll see it has a level of all. And then under all, it has a level called Geography ID. Now, that really isn't what we want. We'd like it to say Geography. There is a relationship between Geography ID and state. And we know what it is. The Geography ID is a key for state. Geography ID is stored in our database as an integer. And by using it as a key for the string value, when the cube is built, the associations can be made in a much more efficient way. How do I get this to say geography, however, instead of Geography ID? Or get it to say state? Or get it to say something other than Geography ID, which it clearly isn't? Well, I can come back to the Dimension Designer, click on Geography ID, right-click and say Show me the properties. And when we come over here, we'll see that it has a name, Geography ID. I'm going to change that to either Geography or State. I think I'll change it to State in this case. We'll see it appears as State. We'll reprocess the dimension. We'll come back to the browser. It tells us that it's been reprocessed, so we have to either reconnect, clicking here, or reconnect using the icon in the toolbar. Notice now we have the geography dimension with a state hierarchy, which is the only one. Under all, we see the states. We never even see the geography ID here, which seems to be a rather nice idea, because the geography ID will be meaningless to end users. So to re-emphasize, we have a geography dimension, a state hierarchy, and this is called an attribute hierarchy because it has exactly one attribute in it as far as depth. We'll see user-defined hierarchies that are going to be stacked on top of each other in the way that we normally think of hierarchies. But these hierarchies are one level deep, except that it is added an all level at the top. So to get down to Illinois here and fully qualify a reference to Illinois, we would say geography.state, state being both the hierarchy and the level, .Illinois. Let's go ahead and add a time dimension. In this case, we'll let the key column be year ID, and we'll let the year name be the name column. As you may recall, the name column contains the year preceded by a CY for calendar year, so it really is a string. The year ID is an integer. We see we're probably going to want to change that year ID to year or something else. Let's go ahead and view it. We'll look at its properties, and we'll see that its name is year ID. Why don't we just go ahead and name this calendar year? So now we have a hierarchy that consists of a dimension, time, a hierarchy, which will be named calendar year. We'll have to see what the levels in the data are. Let's go ahead and process this. If we come to the browser, we'll see that we have the dimension time, the single hierarchy calendar year, because we selected a different name for the time ID column than the key value. And we have two levels, an all level and a calendar year level. There are a couple of other properties I'd like to show you before we proceed any further. One is that if we come back to the dimension structure for focus and look at the property window for focus and focus ID, I want us to come down to the dimension attribute property window, and if we have it sorted by category, we'll see near the bottom there's key columns and name column. And because of the choices that we made in the wizard for designing a dimension, we'll see that the key column is focus.focus and the name column is empty. For focus ID, we see that the key column is focus ID and the name column is empty. But when we go to the geography dimension, we see that the key column is geography.geography ID, the integer, and the name column is the string column that we selected. So if we have a key column that is the same as the name we selected in the wizard, we're not going to have to put anything in the name column. It will be the same. But if they are different, then the name column will have a value. Likewise, the same thing will be true for the time column. If we come in and say that the key column is year ID, then the name column is the year name, which is the name in the underlying star schema relational database table. Now let's go ahead and create the cube, and we come into a wizard. We're going to use an existing table. It's going to ask us which table is our table for the measure groups. And I'm going to come in here and select all of the columns that it has. It has added a column which is the count of rows. And this is often very valuable. I'm going to uncheck it for the time being. It knows that we already have 3 dimensions, so it's going to ask if we want to include them. We do. If we add another dimension to this project later on, we're going to have to manually add it to the cube, because not all cubes within a project will use all dimensions, and it is not added automatically. So I'm going to go ahead and call this my PFE cube. Now, let's go ahead and build the cube. If we say process it, it will realize that it also has some building and deploying to do, and we have skipped that building and deploying. Notice that we have this cube, and it gives us a data source view of the cube, which is really different than the data source view if we look directly at the data source. Notice this is essentially black and white with very little color, but if we look at the cube here, that it has some color in it, but it's still calling it the data source view. Now let's go ahead and browse this cube in the built-in browser in bids. Notice on the left we have something that's going to permit us to drag and drop things into the area here. I'm not so much interested in dragging and dropping them, is seeing what they show. Notice that under here it shows focus, and this is the icon for a dimension, and this is the icon for an attribute hierarchy that has a single attribute in it. Notice that it is 2 columns and 3 rows. Later on we'll see that there is an icon for 3 rows and 2 columns that is part of a user-defined hierarchy that defines the 6th level within the user-defined hierarchy. If we come here, we'll see that under the hierarchy, attribute hierarchy, it shows the members of that, which have an all level and the data. And it also has the focus ID level, which does not have an all level and has the items under it as well. If we go to geography, we'll notice it has a single attribute hierarchy. It has the state level it has the state hierarchy, it has the state level, and this is a single level denoted by a single dot, which will be the top level of a hierarchy, but there's only one level in this hierarchy other than the all level, which doesn't get counted. And then we have the members under here. Notice that if we go to time, we'll have the calendar year hierarchy. Notice it says attribute hierarchy there. Later on, when we create user-defined hierarchies, we're going to see they're just going to say hierarchies. So an attribute hierarchy is a term of art that means a hierarchy that has exactly one attribute in it. We can see the members here, which is going to have an all level. And we'll see that we have items under it. Notice that it's got an ampersand in 2008, and that's something we want to discuss in just a minute. So the point of this demonstration is that we have dimensions, hierarchies, levels, and members. And if we fully qualify a member's name, it will include all of them. Now under measures, we see we have a folder here, and that sort of suggests a hierarchy, but don't be deceived. Folders are not part of hierarchies. They are for convenience of grouping. We can put folders, as a matter of fact, under dimensions. Under measures, we automatically get one. We get a folder for each measure group, and a measure group is associated with distinct fact tables. We can have more than one fact table associated with a cube. So this is not a level. Measures only have one level, and they do not have an all level.
We have now discussed the basis for referencing cells in a cube and touched upon the concepts of attributes, dimensions, hierarchies, levels, and members. We are ready to discuss queries.